Good morning. We're going to start in a minute, just as soon as more people get here. Okay, so you should see Word on the screen. So there's only 8 students here. That's not good. 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 More students. So you have a question about the exam. I'm going to talk about the exam in a little bit. I want to wait till a little bit more into the class. I'm going to do some teaching, and then we're going to talk about the exam, just so people show up late. So when I answer questions about the exam, I want to answer to everyone. That way everyone hears the answer. Also, if somebody asks a question a second time, I'm going to have to repeat the answer, right? So let's hold off all questions about the exam until a little bit into the class, and then I'll say, okay, let's start talking about the exam, okay? Because I know more students are going to arrive late or still arriving now. So I want to hold off the discussion about the exam until a little bit into class. Okay, so this is Red Wano. I can't pronounce your name, sorry. You asked a question about the exam. So I'll answer that and any other question, further into class. But right now, let's just do material and so that, more students are here when we answer those questions. Okay, so, but I will just write the reminder about the exam at this moment, right? So reminder, tomorrow is test 1, right? And it's during class. Test 1 is during class, and we'll start near the beginning of class, right? Right, so class will start. I'll, go over some instructions, and then we'll begin, right? So you need to be here on time. So it is very important that you arrive to class tomorrow on time at 10 o'clock a.m. Okay? Don't be late. Be on time, and that will help everything run smoother, and it'll give you the time you're given to take the exam. Okay, so we'll go back to that. So let's continue our discussion from last class, right? So last class, we were talking about we were talking about chapter 4, right? So this is material not on the first exam, right? Test 1 is on chapters 1 through 3 only. Okay, so we were talking about chapter 4, and so we discussed a few topics. We talked about the Bernoulli distribution. We talked about the binomial distribution. We talked about the hypergeometric distribution, which we're going to talk more about this class. We talked about sampling with and without replacement. Right, and we had examples, right? Okay, so let's continue our discussion about the hypergeometric distribution. And so now let's begin. So this class, we're going to have the definition. We're going to reiterate the definition of the hypergeometric distribution. We're going to talk about, we're going to have examples using the hypergeometric distribution. We had an example last class. We have more. Oh, wait. Sorry, we're going to have, we already did that. So we're going to have an approximation of the hypergeometric distribution, approximation of hypergeometric probabilities. Okay. And talk about the Poisson distribution. Okay. And then we may talk about a little more about other things, but we'll definitely then review for test 1 and also answer your questions about test 1. Answer questions about test 1. Okay. I went over all this. I went over a lot of stuff another day, but we can talk about that. Okay, so so we ended last class with an example, 2 examples: a carton of 24 hand grenades and a group of 15 chess players, right? So let's keep going. Okay, so when n1 plus n2 is large compared to the sample size n, the hypergeometric probability function h of x colon n comma n1 comma n2 may be approximated by the binomial probability function b of x colon n comma p, with p probability equaling to n1 divided by n1 plus n2. If little n is at most 5% of n1 plus n2, the approximation is usually good enough. Okay. Okay, so this is about approximation of hypergeometric probabilities. Okay. Okay, so when n1 plus n2 is large compared to sample size n, then the hypergeometric probability function may be approximated by the binomial probability function with the probability p of success equal to n1 over n1 plus n2. If n is at most 5% of n1 plus n2, the approximation is usually good enough. Okay, so that's because the condition is that when n1 plus n2 is large compared to sample size n. And so that's vague, and so to be more specific, look for little n to be at most 5% of n1 plus n2. Remember, for the hypergeometric probability function, we had a sample space, right? And we split it up into 2 types, n1 many in the first type and n2 many in the second type, right? And so it's the probability that you chose x of the first type and a total of n, right? You choose a total of n, little n many, and the probability that you choose x of them, x of the n are of type n1, and then n minus x, the remaining, are of type 2. Okay, so that's a way to approximate that value. Okay, now, so students have trouble with that. So this is a second, I'm going to write the same thing, but I'm just going to write it like this. So this is the binomial approximation of hypergeometric probabilities. If n1 plus n2 is large and n is small, then h of x colon n comma n1 comma n2 is approximately equal to b of x colon n comma p, where p is equal to n1 divided by n1 plus n2. Okay? And so this is the approximation right here. So when you're studying that, focus on the bold, okay? Binomial approximation of hypergeometric probabilities. If n1 plus n2 is large and little n is small, then this is approximately equal to that, where p is this over that, okay? So example 4.14. Consider a random sampling of 5 students from a sophomore class of 1,000 students. If 30% of them are pre-meds, what is the probability? 3 of 5 chosen are pre-meds. Okay, so consider a random sampling of 5 students from a sophomore class of 1,000 students. If 30% of them are pre-meds, what is the probability 3 of 5 chosen are pre-meds? Okay, so part A, I want you to assume the sample was obtained under sampling without replacement. Okay, so sampling without replacement means that once you choose, every time you choose a student, there's one less student. Okay, you're not replacing the ones you choose. And so we want to find the probability that 3 of 5 chosen are pre-meds. Right? And so we know that because the question is, what is the probability 3 of 5 chosen are pre-meds, right? So that's how we know what we want to find. That's the goal, right? And so just above, we said that the binomial probability function approximates the hypergeometric probability function. Okay. Oh wait, no, never mind. Forget that. So we're just using the hypergeometric probability function at the moment. So okay, so I'm going to copy this, and we're going to go to the whiteboard. Okay, so here's the problem, right? So I'm going to, again, draw a box. Mathematicians like to use boxes to denote sets. Okay, so here's our box, and 30% of them are pre-meds. So what I'm going to do is I'm going to split this 1,000 students into 2 types. N1 is going to be of the first type, and too many of the second type. N1 are going to be the pre-meds, right? So 30% are pre-meds. Right? And then, so that means that 70% are not pre-meds. Okay? So N1 is going to be 30% of the total, and 2 is 70% of the total. Okay, right? And then the total is 1,000. Okay, so the total is 1,000. There's 1,000 students in total. And so if 30% of them are pre-meds and there's a total of 1,000, that means 30% of 1,000 is N1, right? The number of type 1. So 30% of 1,000 is, so that's 3/10 of that. So that's 300. So there are 300 pre-meds out of the 1,000. And then the remainder, 70%, which is 700, are not pre-meds. So we have the values of N1 and N2. Okay. So we have the numbers of each. And so what is the probability 3 of 5 chosen are pre-meds, right? So the probability 3 of 5 are pre-med. Okay, so then that's equal to, so use the hypergeometric probability function. So you want to choose 3, right? So you want to choose 3 people out of a total sample of, you want 3 of type 1, because you want 3 pre-meds, 3 of 5 chosen are pre-meds. And so 3 of 5 here, right? The 3 of 5 here means that the 3 is here. The total sample size is 5. There's 300 of type 1. And there's 700 of type 2. So the probability 3 of 5 are pre-med is equal to H of 3 colon 5 comma 300 comma 700. So what we've done is we've taken this very specific example, right, with a very specific probability involved in that example. And we've thought of it in very general terms. We now think of it as just the value of this function, where we mentioned nothing about pre-meds, non-pre-meds, sophomore class students. None of that is involved in this function. There's numbers, it's a formula. But it's a formula that encapsulates this example and infinitely many other examples, right? So this value will give us the probability that we want. Okay, remember the hypergeometric probability function is H of X colon N little n, comma N1, capital N1, comma capital N2, right? N1 is the amount of type 1, which is 300. N2 is the number of type 2, which is 700 in this example. Little n is the amount of your sample. So our sample is 5. We're choosing 5 out of the total. So that's 5n, and it's 5. And then x is the number of type 1 that you want in that sample. So 3 of 5 are pre-meds. So pre-meds are type 1. And so you want 3 from type 1. So that's 3. Okay, so you see how this probability is equal to the value of this hypergeometric probability function. Okay, so this is H of 3 colon 5 comma 300 comma 700. Okay, and so now you just compute the value of that. And so the value of that, that's equal to I'm going to copy this. Okay, and before, just a reminder, right? The hypergeometric probability function, H of X colon N comma N1 comma N2, that's equal to the probability of in type 1, you choose X of them, and then in type 2, you choose little n minus X of them, and then you divide that by the total, which is N1 plus N2 of either type, and you're choosing little n in total. Right, so when you have a sample size of little n, meaning you have a total of N1 plus N2 things, and you choose n of them, right, what is the chances that little x of them are of type 1 and n minus x of them remaining them are of type 2? That's the formula. And so here you just plug in. So you're going to have, this times this divided by this. N1 plus N2, that's the 300 plus 700, that's 1,000. C, and you're choosing 5, right? And so type 1 has 300 many students, and you want to choose 3 of them, times the 700 that are non-pre-med, C, 700 C2, because then you're choosing the remaining 2 to not be pre-med. So you get that, that's equal to that. And when you compute that, you get 0.13211. Okay. Do you like this better zoomed in a little bit like this? Is that better? Raise your hand. There's an icon that allows you to raise your hand. Press it if you like it better zoomed in like this. Okay, so I don't know what it means if you didn't raise your hand, right? Okay, so put down your hand. So we'll just wait for it to go away. Okay. Okay, so I'm gonna wait for. Okay, yes. So we're all gonna wait for the hands to go away. Wait until the hand. Don't press the hand button now. Okay, so I want to reset this. Okay, because Sean is saying that he does. Okay, so I'm aware of that. Okay, now what I want everyone to do is raise your hand if you don't like it zoomed in. If you don't prefer it zoomed in, you want it the original way. You don't like it zoomed. Raise your hand in that. If you don't like it zoomed. Okay, so nobody raised their hands. Nobody dislikes. Okay, so how do you know which distribution? Yeah, it looks like I understand. How do you know which distribution to use to answer a question? Okay, so good question. Sampling without replacement, right? Sampling without replacement. You're not replacing the students that you choose, right? So that's why in part A, there's assumed the sample was obtained under sampling without replacement. Okay. Now, if assume the sample was obtained under sampling with replacement. Okay, so you now replace the students you choose. So there's 1,000 students, 300 are pre-meds, 700 are not. You want to choose, what is the probability 3 of 5 chosen are pre-meds? But every time you choose a student, that student then goes back into the pool of all students. Okay, and so let's look at this. So the probability 3 of 5 chosen are pre-meds under these new assumptions. Well, it's going to be the binomial probability function. It's going to be 3 colon 5 comma 0.30. And so here's why, right? So if you have 1,000 students, right, and you want, and you choose 5, but each time you choose a student, you have a 30% chance of choosing a pre-med, right? You want to succeed 3 out of the 5 times at choosing a pre-med student. Okay, so right, so same problem, but now, so this is sampling with replacement. Okay, so this is sampling with replacement. Okay, now sampling without replacement. I'm sorry, the last page. That was sampling without replacement. I'm going to put this in green. Sampling without replacement. So it stands out. Okay. Here, we have sampling with replacement. And same question. Right. Okay, so we have the same, okay, so then we have the same box. Okay, so then you have split into two types, right? N1 and N2. 30% are pre-meds, right? So you have 30% pre-med and 70% not pre-med. Okay, so if there's 1,000 in total, that means if 30% are pre-med, that means 300 of them are pre-med and 70% are not, so that means 700 are not pre-med. So 300 of type 1, 700 of type 2. Those are probably 3 of 5 chosen pre-med. So it's sampling with replacement, right? It's sampling with replacement. You are replacing each of them. And so I'm going to put, let's try and do this good. So it's sampling with replacement. So, and so you want 3 of 5. You want 3 of 5 chosen. What's the probability 3 of 5 chosen are pre-meds, right? But every time you have 1,000 and you have a 30% chance. And so that's why this is what we want. We want B of 3 colon 5 comma 0.30. So actually the amount of each doesn't matter. So let me erase this because this is from, you have 30% pre-med, 70% not pre-med. And so that means P, the probability of success P, right, is 30% or 0.30, right? So success is choosing a pre-med student, right? So you choose 5, right? You make 5 selections each time. You have a 30% chance of success of getting a pre-med student, right? Where it's with replacement, and so you always have 1,000 students, and 30% of them are pre-meds each time. The odds don't go down every time you choose a pre-med student, right? Okay, and so this is just telling you, right, that you do this experiment 5 times. Each one's a Bernoulli trial with a 30% chance of success. You want to succeed exactly 3 times. So 3 times you get a pre-med student with a 30% likelihood, and 2 of the other times you fail, which is a 70% likelihood. And so then this is going to be equal to 5 choose 3, right? The number of ways to choose 3 out of the 5 to be pre-med, times the probability of success, which is 0.3 cubed, because you succeed 3 times, and then 0.7, the probability of failure, raised to the second power, you failed 2 times. So that is the probability right here. That's the probability we want. Okay, so let's go back here. Okay, so that's the probability. And so I'm going to write this again. Copy that. Oh, copy this. And so you have 5 choose 3. Then you have the probability of success, which is 0.30, raised to the third power, times the probability of failure, which is 0.70, raised to the second power. And so you multiply all of that. And when you multiply all of that, you get 0.13, 132. Okay, it's very close to the other one. In this situation, right? In this situation, it depends on the situation, right? Because we have 2 different types, right? So you know, in this example, yeah. Okay, so note that both answers have the same first 3 decimal places. Okay, you have 0.1 For A, you have 0.13211, and for B, you have 0.1323. So they're very close. Okay. Okay, so let's talk a little bit about the Poisson distribution, and then we'll review. Okay, so next is 4.5.5, which is the Poisson distribution. And so the Poisson distribution can approximate the binomial probability function when n is large and p is suitably small. Okay, so definition 4.7. Let lambda be a positive constant. The function p of x colon lambda, which is equal to lambda to the x e to the negative lambda over x factorial for x equaling to 0, 1, 2, 3, and so forth is the Poisson probability function with parameter lambda. Okay, a random variable has a Poisson distribution and is called a Poisson random variable if its probability function is the Poisson probability function. Okay, so if you have a random variable and its probability function is of this form, the Poisson probability function, then your random variable is a Poisson random variable with a Poisson distribution. Okay, so you just want to look for its probability function to be of this form. Okay, and this is the definition of the Poisson probability function with parameter lambda. Okay, and so let me put a summary of the approximation statement I made. If little n is large and p is small, so that lambda, which is equal to n times p, is of moderate size, then the binomial probability function b of x colon n comma p is approximately equal to the Poisson probability function of x comma lambda. Okay. Okay, so if you're in a situation that little n is large and little p is small, so that lambda equals n times p is of moderate size, then these two are approximately the same. We have this probability function. I define for you this function, and they're approximately the same value if those things happen. Okay, the statement is fairly simple, but it can be, I guess the function is a little weird. So what I'm going to do is I'm going to give you examples, and then by looking at the examples, you'll see what I mean by moderate size. I think that's the best way to approach it. Okay, let's see. There we go. So let's do an example. Example 4.15. Okay, if the probability is 0.0001 that any one passenger of a subway train will be robbed what is the probability ten of the next 50,000 passengers will be robbed? Use the Poisson approximation of the binomial distribution. Okay. If example 4.15, if the probability is 0.0001 that any one passenger of a subway train will be robbed, what is the probability 10 of the next 50,000 passengers will be robbed? Use the Poisson approximation of the binomial distribution. Okay, so this is what's happening. So every one so just consider the event of being robbed a success in a Bernoulli trial. Okay, so you have any one passenger, and so there's a 0.0001 probability that person will be robbed. That is a success. Being robbed is a success. So remember, I said that success does not mean something good happens. It does not mean something desirable happens. It's just a choice. There's two possibilities, right? It's like binary. There's two possibilities, and you could choose either of them to be a success, right? If you're playing a game of football, right, you either win or lose. You could say a success is winning, but you could also say success is losing, right? If you want to know about how many times, if you're thinking about losses, you could think of a loss as a success. So success is an arbitrary choice between two possibilities. It doesn't mean favorable, it doesn't mean good. Okay, so consider the event of being robbed a success in a Bernoulli trial. Okay, and so that means the probability of success. So that means the probability of success as defined in the problem of any one Bernoulli trial is the chance of being robbed, which is 0.0001, right? So what we want the probability of 10 successes in 50,000 Bernoulli trials, right? So we have the next 50,000 passengers are like each a Bernoulli trial, right? Every passenger of those 50,000 is a Bernoulli trial, where if that person gets robbed, you succeed, and if the person doesn't get robbed, you fail, right? So you have a 0.001%, you have a 0.0001 chance that in any particular person, that person will be robbed, and you have a 0.9999 chance that the person isn't robbed, right? And so we do this each time there's another person, and we do this 50,000 times. And so you want to know the probability that exactly 10 of those 50,000 times you succeed at that person being robbed. So the probability 10 out of 50,000 will be robbed. That's equal to B of 10 colon 50,000. I'm going to not put the comma in. That's 10 colon 50,000 comma 0.0001. Okay, it's the probability that in 50,000 Bernoulli trials you have 10 successes, where the probability of success is 0.0001. Okay, so you can visualize that. So applying the Poisson approximation, we get, so, right, the Poisson approximation is here, right? It tells you that the Poisson probability function is approximately the same as the binomial probability function. And so what we get is that is that function, right? We know the answer is the value of this function. We want to approximate it using the Poisson distribution, the Poisson probability function. And so x is what x was, right? So x is 10, right? But lambda, so we have to think about what lambda is, right? Lambda, so we get from lambda equals to n times p, right? Lambda equals n times p. So n, little n is the total number of Bernoulli trials, right? So little n is the total number of Bernoulli trials. So that's little, so this is little n, right? Okay, so that's little n, right? So little n here, that's little n. N is the 50,000 Bernoulli trials, but the number 50,000. Right? And now you want to multiply that number by p, the probability of success, right? Probability of success in a Bernoulli trial is this. So the probability of success is p here. And so this is going to be times 0.0001. Okay, so I'm going to put the green here also. The 50,000 passengers, that's n. And p is the probability of success of being robbed. That's this. Okay, that's where I'm getting those values of n and p. And so you multiply the two, and so then that times that. Okay, so then that times that, you move the decimal. So this means you move the decimal place over 1, 2, 3, 4 places. So 1, 2, 3, 4. So that's equal to 5. So lambda is equal to 5. So if we get from the fact that lambda equals 5 that, where's the b there? B of, right, the value of this function is approximately equal to this. So I'm going to put little n comma lambda here, just so that, x, sorry. X comma lambda, which is equal to p of, and then x is 10, and then lambda is 5. Okay, and so this is equal to, so now you just follow the definition, right? This is, right? Right, so the equation above, so you can see it in front of you, that was the equation, right? So then you just plug in, this is, x is 10, right? So you have 10 factorial here. Lambda is 5, so you have 5 to the 10th power. And then times e raised to the negative lambda, which is 5. Okay, see that? And so now you compute that, and you get that this is equal to 0.0181. So what we showed is that the probability of 10 out of 50,000 will be robbed is approximately equal to 0.0181. Okay, so the question I want you to ask is, why were we able to approximate the binomial probability function by the Poisson probability function? And so the answer is that the problem met 3 requirements to make that approximation. 1, the first one requirement you need is that little n is large, right? So little n is equal to 50,000 is large. So met that requirement. 2, p is small. Well, what is little p, the probability of success? Little p is equal to 0.0001. So that is small. And 3, the third requirement, that lambda equals n times p is of moderate size. 3, lambda, which equals n times p, which you can see the numbers right there. That's 50,000 times 0.0001, which we calculated was 5, is of moderate size. So someone asked what moderate size means. And so in this example, you can see that 50,000 is large, 0.0001 is small, and 5 is of moderate size, right? And so it meets all 3 conditions. If n is large, p is small, and so that and lambda is of moderate size, if these 3 things happen, then the value of the binomial probability function is approximately the value of the Poisson probability function. Okay, and that answers it. So we made this approximation, and we were able to do that because we met the 3 requirements of this. Okay. So over here, I bolded this part. Okay, and I want to do the same here. Okay. I don't want to put the bar in because it's sort of involved. So I'm going to bold this also. Okay, it's a little hard to read when it's bolded. You can read it though. It's not hard to read. But I'm bolding it so that you look here. Okay, I want you to look at that spot. Okay. And so we met all 3 conditions. If little n is large, p is small, and lambda is of moderate size. If those 3 things happen, then these 2 are approximately equal. N large, little n large, p small, lambda moderate size. Okay? And that's justification for that inequality right there. The bolding, it doesn't matter. Okay, so then this thing, right? So I'm gonna give this another color. I'm gonna give it the color red. That approximate right there, that one thing, that's this. Okay? All of this is to justify that one approximation. Okay, every statement in a mathematical proof requires justification, right? So this approximation is justified from meeting these 3 requirements. I could have just done that, but I did the whole discussion, so it makes sense, right? But I guess logically, you might just look at those 3 things. Okay. Okay, I got black back. Okay. I'm going to do one theorem, and then we're going to talk about the exam. Theorem 4.2, Poisson's limit law. If little p varies with n, so that n times p is equal to lambda, where lambda is positive and constant, where lambda is a positive constant, then the limit as n approaches infinity of b of x colon n comma p is equal to p of x comma lambda. Okay, but now let's talk about, so now let's review for test 1. Okay, so let's review for test 1. So earlier at the beginning of class, there's a question, would you say the exam is similar to the practice exam, right? So let's go to those questions, right? So these are, you should see on the screen, practice questions for test 1, right? These are the 7 practice questions I posted on Blackboard, right? And so hopefully you did them, or maybe you do them today. Right, so I'm not saying that this is the exam, right? I'm giving you questions that will help you for test 1. That does not mean that the questions in test 1 will be these questions, right? And there may be questions different for them. But this is a good way to gauge whether or not you understand the material, whether or not you can answer questions, pertaining to the material of this test, right? So I'm not promising you that the exam is the same as this, okay? But this is helping you. This is definitely helping you prepare. That's the answer to that question. Okay, so does anyone have questions about these 7 practice questions for test 1? Does anyone want me to go over any of these 7 problems? Okay, I'm going to go in order of the questions. So number 7. Okay, I'm going to go over number 7 first, and then number 5. So let's go over number 7 first. Okay, so for number 7, let A, B, and C be events. So P of A equal 0.6, P of B equal 0.3, P of C equal 0.4, P of A B equal 0.2, P of B C equals 0, and P of A C equal 0.1. All that given. Find each of these probabilities, right? Okay. So I'm going to copy this, and we're going to go to the other screen. Okay, that's the question. Okay, it's just not centered. Okay, let me do that. There we go. Okay, so A, B, and C are events. So P of A equals 0.6, P of B equals 0.3, all this, and find these 4. Okay, so let's do part A. So the probability of AB prime given C prime is equal to, right, the probability, definition of conditional probability. This is equal to the probability of AB prime and C prime divided by the probability of C prime, right? And so it's just a matter of finding that probability, right? So if the probability of C, the probability of, how did I do that? So if the probability of C is equal to 0.4, well, that implies the probability of C prime is equal to 0.6. Okay, so I'm going to quickly just plug in my charger because it's running low on battery and it's slowing down now. Okay, give me 1 second. Okay, I'm back. Okay, so Probability of C equals 0.4 implies probability of C prime is equal to 0.6. Right? And so we know the denominator is 0.6. I did that first because it's the easier one. Now P of A, B prime, C prime. Okay, so let's go to the whiteboard. Okay, so now let's do a Venn diagram. So there are three sets. There's A, B, and C. There's A, there's B, and there's C. These are all circles. This is A, this is B, and this is C. It's best to start from the inside out. So there's no A, B, C. So, okay, so we have BC equals 0. Okay, so I have the problem in front of you. Probably a BC equals 0. Oh, you know what I can do? I guess I can copy this. Maybe I can copy it. Okay, so there's a little overlap here. So set A is the circle B and C. Okay, so P of A is 0.6. Good. Okay, BC is probably BC is 0. This is like the biggest thing that it's being told to you. That means that there's nothing, there's no chance of B intersection C happening. Okay, so now when you get the probability of A and B is 0.2, that means the probability of being in just this region is 0.2 because there's no chance of it being here or here. So A and B is this thing, but it doesn't include this. So you don't need A, B, and C. This is a trick question. A and C is 0.1, but this is now, there's no chance of that happening. So this is 0.1 here. Okay, and now the probability of A is 0.6, but this is already 0.3, so the remaining is 0.3 that's in neither B nor C. Then probability of B is 0.3, but there's a 0.2 here already, and so you need an additional 0.1 so that everything in the circle adds up to 0.3. And then P of C is 0.4, this is only 0.1, there's no chance here, so that means that you need a 0.3 in this chance of this in this region in order to add up to 0.4 in total. Okay. It adds up to 1, right? You have tenths, 1/10, 2/10, 3/10, 1/10, 3/10, 1, 3, 6, 7, 10. So there's no chance that's in none of the sets. Okay, it's no chances in none of the events. So it has to be in at least one. Okay, so so in part A, it says so we want P of A, B prime, C prime, P of A, B prime, C prime. So now it's easy. What's in A, not in B, and not in C. So that this probability is this. It's in A, not in B, and not in C. So it's 0.3. Okay, so that's 0.3. And so if we go back here, we have 0.3 over 0.6. And this is equal to 1/2, which is 0.5. It's equal to 1/2, which I like more because it's a fraction, and it's equal to 0.5. Okay, and so that's part A. And then if we look at part B. I don't know if we need to do every part. P of A given B, by definition of conditional probability, is P of AB divided by P of B. And so P of B was given to us as being 0.3 in the given, right? Now P of A and B, put here, and we're just going back to the whiteboard. Everything is now pretty much just looking at the whiteboard now. So P of A and B is this region, right? P of A and B is the probability it's here, right? So P of A, B is the sum of the probabilities of those two disjoint regions. There's a 0 chance here and a 0.2 chance there, so it adds up to 0.2. Make sense? So So the pink region was just this one part, but the blue is this and this, but there's no chance here, so it's only the 0.2. So P of AB is 0.2, and so you have 0.2 over 0.3, and so that's equal to 2/3. And 2/3 is a decimal, is 0.66666, or 0.67 rounded to the hundredths place. Okay, let's do C. So we have the probability of C prime B given C prime. That's equal to the probability of C prime and C prime B and C prime, but that's just probability of C prime B divided by the probability of C prime. That's equal to, I'm just going to simplify the numerator first. It's P of C prime B. You don't need two C prime. C prime and C prime is C prime, right? So C prime and B. That's that. And divide by probability of C prime. And so then that's equal to, and what's the probability of each? Probability of C prime I wrote up here. It's 0.6. So that's 0.6. And then the numerator is probability of C prime B. Probability of C prime B. So the probability of C prime B. Not in circle C, but in B. So it's not in C, but in B. That's here. See that? It's this thing plus this thing. That's not in circle C, and it is in B. So that adds up to 0.3. So that probability is 0.3. Once you draw the Venn diagram and you see that, you see all the probabilities, you know, the 1 is 0. So you do that, all the rest of it's automatic. 0.3 over 0.6 is 1/2. That's equal to 0.5 as a decimal. Okay, and then D, what's the probability of B prime given A union C? So that's equal to the probability of B prime and A union C divided by the probability of A union C. Okay, so by putting A union C here in parentheses next to the B prime, like you're multiplying them, I mean and. So this is B prime and A union C. Okay. Let's do the denominator first, because that looks easier, right? So P of A union C. We can go to the whiteboard again. We want the probability of A union C. So A union C, let's use another color. Let's use orange. This orange up here. Probability of A union C. Where's A union C? This is A. This is C. So it's in one circle or the other. And so this circle, you have this here, you have this here, you have this here, you have this here. The x's don't contribute anything. So you just add up those. These are the probabilities in A or C, right? This 0.1 is not in A or C. So you have 3, 5, 6, 9. You have 0.9 chance. Probability of A union C is 0.9. That's A, right? Circles A, this is B, this is C. So you add up the ones I circled in orange. The numbers I circled in orange. 0.3 plus 0.2 plus 0.1 plus 0.3. That's 0.9. I'm not including that, okay? So that's 0.9. So the denominator is 0.9. And now the numerator is B prime and that set. B prime and that set. So now we want the probability of B prime and that set. So maybe, let's see, does this color stand out? The probability of B prime and A union C. So A or C is the orange region, right? But we want it also to be not in B. So it has to, I have exclude this point too. So that's this region. You have, it's in A, not in B. A or C, not in B. So it includes this one, and this one. These three that I circled in purple are in A or C, and they're not in B. So I'm excluding now point 2 also. I already exclude point 1 in A union C. Now I'm also excluding point 2 because it's in B. It has to not be in B. So you add up these three, point 3 plus point 1 plus point 3, and you get 0.7. Okay, so that's 0.7. The odds of that are 0.7. And so here you have a 0.7. So 0.7 over 0.9 is equal to 7/9. And 1/9 is 0.11111. So this is 0.778. And then you round it to 0.778, let's say. And let's round this to 3 decimal places. So 2/3 is 0.667 here, okay? In the test, I'm going to tell you to round to 4 decimal places correctly. So you know what? I'll do 4 here. So this is point, and then that, okay? So, so there. So I'll say 4 decimal places on the test, and so I'll do that here. This is 2/3 rounded to the nearest 4th decimal place correctly, and then this is rounding to 4 decimal places correctly here. So that if you do it as a decimal, you could write it as a fraction on the test, and it's right. So if you write 2/3, you're right. And if you want to round it to 4 decimal places, it's 0.6667. And if you want to round 7/9 to 4 decimal places, 0.7778. But notice how fractions are much more illustrative of the number you want than decimals are. 2/3 is much more visual than 0.6667, right? 0.6667 doesn't really visualize 2/3 as much as a fraction does. Okay, so that is number 7, not number 1. Right, that's number 7 on a review sheet, right? So I'm looking at the review sheet. That was number 7. And so I answered that question. Yes, so you can leave in fractions. Okay, so the other question was number 5. So the next question I see is number 5. So let's talk about number 5. Number 5 is this question. In how many ways can there be a first place, second place, and third place winner in a race with 20 runners? Note that there are no ties. Okay, so I'm going to copy this. Okay, so let's go to now lesson. This is number 5. It's going to delete. Okay, in how many ways can there be a first place, second place, and third place winner in a race with 20 runners? Note that there are no ties. There we go. Okay. Okay, so the solution is simple. Let me illustrate on the whiteboard. Let me copy this. Go to the whiteboard. Okay, so okay, so in how many ways can there be a first place, second place, and third place winner in a race with 20 runners? Note that there are no ties. Okay, so there's no ties, so there's a definite first, second, third place person, right? So, okay, so let's say that's first place. Let's say that's second place, kind of like hangman. It's not really hangman though. This is third place, right? And then you keep going in the race, right? So there are 20 runners in total. There are 20 runners in total. So how many choices do you have for a first place winner if there are 20 runners? How many people could win first place? I'm asking the class, right? You could say it out loud. You don't have to put in the chat. 20, right? Good. There are 20 people who could win first place. Now, this is without replacement. We're not replacing the runners, right? Once you come in first place, you can't also come in second place, right? So this is an example of sampling without replacement. So how many people could come in second place after someone already came in first place? 19, right? Once somebody crosses the finish line, that person, once somebody crosses the finish line first, that person is now first in the race, right? There are 20 people who started the race, so 20 people could have come in first. Once that one person, and there can only be one because there are no ties by assumption, once that one person wins, there are now 19 other people who could possibly come in second, right? And so there are 19 possibilities in that exact moment in time. Even if somebody's right behind them, what if they stopped, right? Something weird, right? So all the other 19 other people have a chance now at winning. Now, after that next person comes in second, how many people could come in third? 18, right? So now there are 18 people left who can come in third place. Right, so you're just subtracting one, right? Each time there's one less person who could then also finish the race. So the answer to how many ways can there be a first place, second place, and third place winner is just 20 times 19 times 18. And so you multiply those numbers and you get the answer. So 19 times 18. I don't like to use calculators. On the test, I wouldn't blame you for using calculator. I don't like to use calculators. So 9 times 8 is 72. 8 plus 7 is 15. That's 152. 0, 1 times 9 is 9. 1 times 1 is 1. You add them up, and you get 2, 14. Carry the 1. There's 3. So you get 342. 19 times 18 is 342. Then 342 times 20, you don't actually have to multiply this out because you know, if you multiply it by 2 and add a 0, that's it, right? So 2 times this is 684, and then you add a 0. So this is equal to 6,840. That's the answer. If there were ties, it'd be very complicated. So don't worry about it, right? It's not the test. The test is not about ties, right? Let's not make the test harder, right? Okay, so I'll get to that in a minute. That's a separate question, right, than this question. That's not this question. So I'll answer that after we're done, right? So I want to stay on topic with each question. So you can hold your questions until the current question's done, but I answered. Yeah, never mind. Okay, so number 5 is 6,840. 6,840. So the solution is 20 times 19 times 18, which is 6,840. Is that what I said? 6,840. 6,840. Good. 6,840. Good. So that's number 5. Okay. So we're back here. So there was another question. There's one current question. Okay. Any hint on how to know if I should use permutations or combinations? Okay, that's the question. Okay, so question. Okay, so the question is, any hint on how to know if I should use permutations or combinations? So I'm just going to correct grammar. Okay, so any hint on how to know if I should use permutations or combinations? My answer to that question. Okay. Okay, so on the test, I'm not going to necessarily tell you which to use, right? On the test, I will probably, definitely, I will probably not tell you which one you should use, right? It will probably be up to you to figure out whether to use permutations or combinations, right? Right. So so you'll probably have to figure it out. Now there's a difference, right? So when order matters, right? You use permutations. Right? When order matters, use permutations, right? Okay, so I'll get the next question after this one. When order matters, use permutations. So right, and so when order doesn't matter, does not matter, use combinations. Okay, so that means the question is answered. The question of whether to use permutations or combinations boils down to recognizing in the problem whether order matters or order does not matter. If you can answer the question correctly, whether order matters or order does not matter, then you have answered the question of whether to use permutations or combinations. Okay, so that's the simplest, best answer I can give you to that question. That if you recognize that correctly, that the problem involves order, then you use permutations. If you correctly recognize the problem involves something where order doesn't matter, then you use combinations, right? And there are some problems where you could see it in two perspectives. You could take the perspective where you can get where order matters, and you use permutations, and you can take the perspective where it doesn't matter, and you can use combinations, right? And so you get the same. If you do each correctly, you get the same answer, right? Okay, so for the problems where it's only one or the other, you have to recognize which one it is. Okay. Okay, so I think that best answers the question, right? And in order to be able to do that correctly, you just have to do examples, practice examples, in which you're required to figure out whether it's permutation or combination. So the best way to be able to do that, the best way to learn how to distinguish between which problems use permutations and which use combinations, or as I just said, which problems involve order and which don't, or which do not, is to just do more examples, right? The more examples you do, the more you get right. Just do more examples, I should say, correctly, right? If you're doing them incorrectly, it's not. Though it hopefully leading you to doing it correctly. But if you can do a bunch correctly, the more you can do correctly, the more likely you're going to get right in the test. Okay, so that's the answer to that question. Okay, so did I answer your question about that? Does that answer it? Do you have a further question about that? Asib, you asked about. Does that answer your question?
Yep, it answers. Thank you very much.
Okay, you're good. Okay, you're welcome. Okay, so Weizhen and Zhao, could you do question 2? Sure. So next, let's do question 2 on the sheet. So number 2 is here. Okay, number 2 is here. Okay, this. That's group formatting. Good. Just delete it. Okay, so number 2. Let me just get rid of this excess stuff for a second. You have a second place winner. get all like lead in this now. Okay. Okay. So a card is drawn at random from a standard deck of 52 playing cards so that each card has an equal probability of being drawn. So hopefully you've read this already. Find the probability of drawing a card that's neither a club nor a 7. Okay. So 52 cards, each one is equally likely to be drawn. Probability card is neither a club nor a 7. Okay. So let's go to the whiteboard. Club or 7. So these are the clubs, and these are the 7s as a set, right? And then so this is the universals. This is the sample space outside of it, right? This is the deck of 52 cards. Okay, so you have an experiment where you take one card from a standard 52 card deck, right? Each card you could choose as a sample point of the sample space of that experiment. So there are 52 sample points in the sample space, but all 52 cards, right? And so what we want is the probability of a club or 7. So let me just back here again. Probably the card is neither a club nor a 7. Opposite. Probably is not neither a club nor a 7. Probability of neither club nor 7 means not club. And not 7. So not club and not 7. Okay, but first let's think about the standard 52 card deck, right? So how many clubs are there, right? So there are 13 of each suit. So there are 13 clubs, right? There are 13 clubs in total. You need to know the composition of a standard 52 card deck for the test, right? There are 4 7s. There's 4 of each type. There are 13 types: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, right? There are 13 types. Each of them have 4 cards, 1 in each suit. So each of the 13 types, there's that type in hearts, spades, clubs, and diamonds. So each of the 13 types has 1 card of each suit. So 13 times 4 is 52. That makes up the entire 52 card deck. Okay. As a side note, a face card is a jack, queen, or king. Only jack, queen, or king, not an ace, right? So a face card is either a jack, a queen, or a king. There's 4 jacks, 4 queens, 4 kings. There's a total of 12 face cards. You might want to write. This is in the notes, okay? So a total of 12 face cards. Okay. But anyway, back to here. There's 13 clubs. There's 13 of each type. There's 13 of each suit. Each type has 1 of that suit. So there's 13 of each suit also, right? And also, right, there's 26 black cards and 26 red cards, right? The 26 black cards are 13 clubs and 13 spades. The 26 red cards are 13 hearts and 13 diamonds. I wrote this all down, right? It's there. If you can go back, I wrote down the composition of the deck. Okay, so you have 13 clubs and 4 7s. Okay, so the 7 is 1 of each suit, right? There's exactly 1 7 that's a club. So there's 1 card in the intersection of the set of clubs and the set of 7s. There's 3 other 7s that are not clubs. There's 13 clubs in total. 1 of them is a 7. And so the other 12 are not 7s. So you have 12 clubs that are not 7s, 1 card that's a club and a 7, 3 7s that are not clubs. You add this up and you get 16 cards. There's a total of 52 cards in the deck. There's 16 here. 52 minus 16 is 36. There are 36 cards that are neither a club nor a 7. See that? The Venn diagram shows you that. Okay, so again, there's 12 cards that are clubs, not sevens. There's one card that's a club and a seven. There's 3 cards that are sevens, not a club. And there's 36 cards that are neither a club nor a seven. Okay, so this Venn diagram illustrates all of that, this one picture. So probability of not a club and not a seven. Let's C be the event of being a club. And S, make S the event of a seven, of drawing a seven, okay? So I've now defined the event C and the event S. So the probability of not a club and not a seven is the probability of the event C prime, S prime. The probability of not getting a club and not a seven. Okay, well, that's equal to the number of cards that are in the event C prime, S prime, divided by the total number of cards in the deck. In other words, N sub C prime, S prime are the number of cards that are not a club and not a seven. So what cards are not a club and not a seven? That means it has to be outside of the set of clubs and outside the set of sevens, right? So there are 36 cards that are not a club and not a seven. And so that means that the numerator here, this number, that's this. So that means it's 36 divided by the total 52. There are 36 cards that are not a club and not a seven, divided by the total number of cards in the deck, which is 52. That's the probability of getting a card that's not a club and not a seven. Okay, so that's the answer to that one. Okay, so I'm going to keep going with this question first before I answer the questions. So we have 36 over 52. Okay, so let me move this. Okay, so the answer, so for part A, right, we have the probability of not a club and not a seven. That's equal to, as I wrote down the whiteboard, little n sub C prime S prime. Okay, let's have the formatting for that. Little n sub C prime, little n sub C prime S prime, and divided by the total number of cards in the deck. And so, right, that was 36 over 52. Okay, and if you simplify that, so I want fraction, the simplest form for it. So you have 18 divided by 26. This is equal to 9 over 13. Okay, as a fraction. Okay, this is illustrated on the whiteboard. Okay, so now B. So B, we want the probability of a jack or queen or king, right? It says find the probability of drawing a jack, queen, or king. So the probability of a jack or queen or king. Right, so that means that it's the probability of a jack plus the probability of a queen plus the probability of a king, right? Because drawing a king, jack, queen, or king, these are mutually exclusive events, right? So let J equal the event of drawing a jack. Q equal the event of drawing a queen. And K equal the event of drawing a king, right? Usually you want your notation to be easy to follow. So I'm using the letters that correspond with the first letters of those words, right? Right? So drawing a jack or queen or king are mutually exclusive events. So J, Q, and K are mutually exclusive events. Right? You cannot draw two of these cards at the same time. Right? When you draw one card, that one card cannot be a jack and a queen at the same time. It cannot be both a jack and a king at the same time. It cannot both be a queen and a king at the same time. All three of these events are mutually, it cannot be a jack and queen and king at the same time, right? So these three are mutually exclusive. So the probability of one of them, probability of jack or queen or king, is probability of jack plus probability of queen plus probability of king, because the three are mutually exclusive events. They cannot happen at the same time. And so the probability of finding one of them happens is the sum of their probabilities, right? Jack, queen, king are each one type, right? Each type has 4 in the deck, right? 1 for each suit. So each type has a heart, a diamond, a club, and a spade. So each one has 4 out of the total 52 in the deck. So the probability of each is 4 over 52. So the probability of jack plus probability of queen plus probability of king is 4 over 52 plus 4 over 52 plus 4 over 52. And that's equal to 12 over 52. And that's the answer. And so if you simplify, you get 6 over 26. And simplify 30, you get 3 over 13. That's it. Right? And 3 over 13 corresponds with, there's 3 types out of the total 13 types. But really the way to do it is this. Okay. Okay. And actually, I'm going to introduce the notation so you become more familiar with it. So I'm going to add now in an earlier step. And so the earlier step is that the probability of a jack is n sub j divided by capital N plus n sub q divided by capital N plus n sub k divided by capital N. Okay, so the probability of let's move this over. Okay, so probably jack or queen or king is probably of jack plus probably of queen plus probably of king. That's n sub j over n plus n sub q over n plus n sub k over n. Number of jacks 4 over the total number of cards in the deck 52, plus the number of queens in the deck 4 over the total number of cards in the deck 52, plus the number of kings in deck 4 over the total number of cards in deck 52. They have the same denominator, so you add the numerators. 4 plus 4 plus 4 is 12. 12 over 52, that's 6 over 26, that's 3 over 13. That's the answer. Okay. That's B. C. Okay, so C, it's find the probability of a black card, right? Okay, so we want to find the probability. So let capital B be the event of drawing a black card. Okay, so then the probability of a black card, probability of drawing a black card, according to our notation, is the probability of B, the event B, which is equal to the number of cards in the deck that are black cards divided by the total number of cards in the deck. And so how many cards are black in the deck? There's 26 divided by the total 52 in the deck. 26 over 52 is 1/2. As a decimal, it's 0.5. Okay, so that's part C. And then part D, a red jack, probability of a red jack. So I'm going to let R equal the event of a red card. And still, I'm going to keep the notation that J is the event of a jack, drawing a jack. Okay, I had J here for jack. I'm going to keep that. So we want the probability of a red jack. Okay, so the probability of a red jack. So I want you to see how the notation is really quite beautiful. So the probability of a red jack, right, is the probability of the event RJ, right? The probability of a red jack, probability of the intersection of the events R and J. This is equal to N sub RJ divided by capital N, the total number of cards in the deck. It's the number of cards that are both red and jack divided by the total number of cards in the deck. Okay, and so how many cards are both red and jack? So there are 4 jacks, right? 2 of them are red and 2 are black. Okay, so there are exactly 2 red jacks. Okay, and so that means that the notation n sub rj, the number of red jacks, is equal to 2. There are 2 red jacks. And so now this is going to equal the fraction 2, number of red jacks, divided by the total number of cards in the deck, 52. That's 1 divided by 26. That's the answer for part D. Okay, so that's A, B, C, and D for number 2. Okay, Ways and Zhao, did I answer your question? For question 2, did I answer? Do you have further questions? Is something you understand from that question? That's good. Okay, yeah, it means good. Okay, so good. You're welcome. And then so Hasib, you have an image here.
You can just click on it and it would open up.
Yeah, but it's on the internet, so I don't feel comfortable clicking just as a general, not you specifically, just as a general policy. I don't think I feel comfortable clicking on a file.
Okay, yeah, sure.
Can you tell me what the question is?
All right, 1 second.
Yeah, it's a new lap. It's a nice laptop.
So 5 cards are dealt to a player from a standard 52 card deck. Find the probability that he does not get a flush.
Probably that what?
That he does not get a flush.
Oh, probably not a flush?
Yep.
Oh, okay, sure. But okay, so yeah, I guess that could be a relevant question. I want to keep the topic on what's on the exam. So I mean, I guess that's possible. Okay, so I'm going to quickly talk about that. I don't want to spend too much time on that. I mean, that's possible, but it's not on the review sheet. Okay, so question. Okay, student question. Let me put a student question. Okay, what is the probability of not getting a flush? I'm going to put capital not getting a flush. Okay, and actually here earlier when I answered the other question, I'm going to put student question. Okay, so student question. What is the probability of not getting a flush? Answer. Okay, so to find the probability of not getting a flush, find the probability of getting a flush, and then subtract it from 1, right? So if you find the probability of getting a flush, just do 1 minus that, and that's the probability of not getting a flush. Okay, so let capital F equal the event of a flush. Okay, and so that means that the probability of not getting a flush is equal to the probability of F prime not getting a flush, not a flush. That's equal to 1 minus the probability of getting a flush. Okay, and so our goal is going to be to find the probability of a flush and then just plug it in. Okay, so now, so the goal is find the probability of a flush. Okay, so I already did this. I did this probability in class. I'll do it again. So find the probability of a flush. To get a flush, 2 things have to happen. One, first, let me put this as first. First, you have to choose. Remember, it's a poker hand, right? So just put a reminder here, right? A flush is a poker hand in which you get all cards of the same suit, right? A poker hand consists of exactly 5 cards chosen out of the total 52 cards in the deck. Okay, So poker hand is 5 cards from the standard 52 card deck where all the cards are the same suit. Okay, that's a reminder what a flush is. Underline that. A flush is a poker hand in which you get all cards of the same suit. A poker hand consists of exactly 5 cards chosen out of the total 52 cards in the deck. So I defined each separately. That way you would just know, right? A poker hand is 5 cards. Okay, so to get a flush, 2 things have to happen. First, you have to choose 5 cards of the same suit. Right? So you have 5 cards of the same suit. Second, let me wait. That's the whole thing. You have to choose a suit. There we go. The first thing that has to happen is you choose a suit. So if you have the ace, 2, 3, 4, and 5 of hearts, that's a flush, right? But it's a flush because 2 things happened. One, they were all the hearts. They were all hearts. And then the second thing that happened is that you choose 5 cards from that suit. Okay, so if you have the ace, 2, 3, 4, and 5 of hearts, first you chose hearts, and then second, there's 13 cards that are hearts, and you chose 5 of them. Okay, and it's that simple. Okay, when you make those 2 choices, you have all of the flushes. Not only when you choose a color and then 5 of the 13. Not only when you choose a suit, right? One of the 4 suits, and then choose 5 out of the 13 of that suit. Not only is that always a flush, that also exhausts all possible flushes. So by making those 2 choices, every different way to make those 2 choices results in a different flush. It's a flush, it's a different flush, and it exhausts all possible flushes. So counting the number of ways to first choose a suit and then 5 cards from that suit out of the 13 exhausts all is the exact number of flushes. So you have to choose 1 out of the 4 suits. Did I say so suits? Okay, suits. Okay, and then you choose 5 cards out of the total 13 from that suit. And once you do those 2 things, you now have a flush. And so counting the number of ways to make those 2 decisions is also counting the exact number of flushes. Okay, so the number of flushes is equal to okay, so we'll end class, I guess, after this. I go over this last question. Then I'll just talk about something else. So the number of flushes is you have 4 cards, you have 4 suits, you choose one of them of that suit. After you make that, you then multiply it. The number of ways to make those 2 decisions is the number of ways to make the first decision times the number of ways to make the second decision, right? So it's 4C1, number of ways to choose one of the 4 suits, times 13C5, the number of ways to choose 5 out of the 13 cards of that suit. Okay, so another way, think of all 52 cards. Imagine you had all 52 cards on a table in front of you, all 52 cards. Let's say, okay, you look at there's 4 suits, you choose one of them, okay? So that's 4C1. Now get rid of all the other 39 cards that are not that suit. You have 13 cards now on the table of that suit, okay? Now look at the 13, choose 5 of them. You now have a flush, okay? And you have 13 of them, you want to choose 5, 13C5. Okay, so you have 52 cards, you choose a suit, 39 of them are gone, you have 13 left of that suit, then you choose 5 of them, of those 13, that's a poker hand, that's a flush. All of them are the same suit. So 4C1 times 13C5, and you multiply them and you get the number of flushes. Okay? Now, so the number of poker hands, it's not the number of cards, it's the number of poker hands, right? That's the denominator, right? So the number of flushes, right? That's equal to, so n sub capital F is equal to the number of flushes. Capital N is equal to the number of poker hands, right? So P of F, the probability of a flush, is equal to the number of flushes divided by the total number of poker hands. Okay, so the numerator here is this times this. And then the number of poker hands is, well, a poker hand is just choosing 5 cards out of the 52 in the deck. And so you have 52 cards in the deck, and you want to choose 5 of them. So that's 52C5. And so that's the denominator. Okay, so that's the probability of getting a flush. This divided by this. And so you just take that number, and so you get 1 minus that number. And you calculate it, and that's the probability of not getting a flush. Does that make sense?
Yeah, thank you.
You're welcome. Okay. Okay, so I answered all the questions you asked. We're out of time. We went past the time, but you guys want to review, right? So, okay, so I was saying, Blackboard Collaborate Ultra we meet, right, for additional review. I'm thinking instead I can just keep going now, right? But class is over now. So, though before you go, I just want to say again, reminder: test 1 is tomorrow morning at 10 o'clock a.m., right? Okay, be on time, okay? You need Zoom downloaded on the device you are using to take the exam. Okay, have in front of you, right? Not somewhere, have in front of you at least, you can have more, at least 10 pieces of paper, right? Pens or pencils, whichever one you're using, or both. Pens or pencils, erasers if you're using them. If you're using erasers, if you're not using erasers, you're not using pencils, you don't need erasers, right? A watch, if you want to watch to keep track of time, a watch or a clock on the wall, right? Or a clock, right? Some kind of keep track of time. Okay, a calculator, at best, a TI 84 plus, right? So have these things available to you, right? Have a fully charged computer / the device you are using to take the exam. Okay. Also have a charger readily available for that device, unless you're using a desktop, right? Unless using a desktop, right? Or some kind of device that doesn't need a charger, right? If you need a charger for what you're using, like you're using a laptop, I have a charger, have it right in front of you so you can quickly plug it in, right? And have it so that you, without like moving, getting up, you could do it, right? If you need to get up to charge it during the exam, you can tell me in the chat, I need to charge my computer, something like that. I'll let you do it, okay? That's not a problem. But have it ready, right? Don't have the charger in a different room. You have to go get it, right? Have it right in front of you so that way you can do it quickly, okay? All the instructions I gave before apply, right? So you're going to email me the exam after the test is over. Make sure that you know how to send an exam, right? Make sure you are ready and know how to, and have practiced how to send me your exam answers after the exam, right? So I want you to email them to me. You can use, it's called Genius Scan. It's a phone app, right? And so if you have a cell phone and you can download apps on it, like an iPhone, but I think you can do it with other ones. You can use Genius Scan, download it on the app, download the app, and you can take pictures, and then Genius Scan will save it as a PDF file, and you can email to me as one PDF file in one email, okay? It's better if you do something like that, because if you take pictures of your phone, it takes up more space. And so I want each answer in a separate piece of paper, right? And so if you give me 5 pictures, you're gonna have to, it takes 5 emails to do that. You'd have to do email 1 out of 2, 2 out of 2. When you take a picture, don't take a picture of multiple pages at the same time, right? So if you're saying, okay, I don't have enough space to take 5 pictures because you're not using Genius Scan or something else, so let me take all the pictures of all the pages in one picture. It defeats the purpose of taking the test in separate pages, right? You're answering it in a separate piece of paper so that I can read your answers easier and I can differentiate between your answers, right? So don't take a picture of multiple pages in one picture, right? Separate picture for each one. Worst case scenario, if you can't do it in just one email, if you can't do it as a PDF file, then send me five emails, right? But the subject of your email will be first name, your first name, not the word's first name, last name, your last name, right? Math 241, summer 2021, email blank out of blank. Don't write blank out of blank. What I mean is email, fill in the blanks with the email. So if you're sending me 5 emails, right, then the first email is email 1 out of 5, email 2 out of 5, email 3 out of 5, email 4 out of 5, email 5 out of 5, right? Backwards engineering, so you know how many emails you're going to send, right? Try to know how many emails you're going to send, okay? That way, I know that when I'm getting your emails, that I get all of them, right? If you're sending 2 emails with your exam, and you don't put that at the end, I don't know that when I see 1 email, that's not your whole exam, right? Or if you send 3 emails and I get the first 2, I might think your entire exam is 2 emails if I didn't get the third one, right? So make sure to tell me this way. The subject will be like this, okay? I'm gonna bold this, because to me, this is very important. Because when I get 30 exams at the same time, 20, 30 exams at the same time, the subject of the email is really important. It helps me organize it. It helps me make sure that I get all your exams. I always get everyone's exams, and there's never a problem. I'll do it right at my end, but you're making my life way easier, and you're helping your own cause if you follow the subject exactly like this. First name, comma, last name, your first name, comma, your last name, math 241, summer 2021, email blank out of blank. And that would just make so much better for all of us if you do that. Yes, that's my email, and my email address, the email address will be, the email address is, and always will be for this course, Michael Pendazis, summer 2021 at gmail.com. Hold on, we were finished. Okay, the email address is MICHALPANDAZIS, another S, UMMER 2021 at gmail.com. Okay, good. That is always the email for this course. Okay, for every exam, including the final. Okay, every day, every week, this is always the email for this course. Okay, so this test and every future. And when you send the email, make sure to CC to yourself. Make sure to CC or BCC the email you send me with your exam to yourself. Make sure to CC or BCC the email you send me with your exam to yourself. Okay, that way, if you get the email you send, that's like a check to make sure it went out. Okay, and also when the exam is over, about 45 minutes or a little more after that, your exam will be due. And then I'll tell you the time when the exam is over. There'll be a meeting afterwards where we can meet. I'm going to send the link via the Blackboard. The email you have associated with Blackboard, that's going to be where I send the Zoom link. I'm going to send it right before it starts, but I'm going to tell you what time it starts. You'll open it, you'll attend, and then you can ask me whether or not I received the email with your exam answers, okay? Okay, so there will be a Zoom meeting about 45 minutes after the exam is over, okay? You can ask me any question about the exam there. Now, the point is that is when you can check with me whether or not I received your exam answers, right? Okay. If I did not, or I do not see it, or I do not find it, or if there is a problem with how it is sent, I will just ask you to resend it. This is during this meeting, right? The next day or a week later, you can't tell me if I sent you the exam, did you get it, or something like that, right? A week later, even 2 days, maybe 1 day later, this is too late, right? But 45 minutes after the exam, I have the meeting. You come to it. You tell me, did you get my answers, right? Is there any problem? Is everything good? I say, yeah, everything's good. I got your exam. All your answers is good. Or if there's a problem, I'll just say resend it. Not a problem. But if you don't come to the meeting, if there's a problem, it's not addressed, and days go by, or even the next day, because that's late, there's not much I can do. I could give you a makeup, but you're not going to, that exam is now moot, right? I can't grade that exam anymore. It's too much time gone by. Okay. So it's very important that you attend that meeting 45 minutes after so we can check. Okay. So I think that pretty much covers everything. I'm going to go over everything again. If you go on Blackboard and you go to the test link, there's 2 files there. Read them and they can answer, I think, every question you might have. Okay. There's no questions during the exam. Before the exam starts, I'm going to put the test on the screen, and I'm going to ask you not to start, but just read the test. Make sure you can read everything, okay? So if you can't read something, if you have trouble seeing something, you tell me before the exam starts, I'll address it, or I'll have everyone write it down, okay? But during the test, there's no questions, so you're really not supposed to tell me during the exam that you can't read something or something like that, okay? The exam is written well, so I don't think there's any problems with the exam. Usually when students say, like, oh, this doesn't make, usually a student just doesn't understand the question, has to think about it, right? So it's a test, you have to answer the questions, right? So I can't tell you what a question means, right? But before the test, if there is a problem, you can address me before. If there is, I'll fix it or address it. There probably won't be, okay? I think that covers everything. We can go now. If you need to go, if you want to go, you can leave now. If you have more questions about the exam, you can stay, right? Keep in mind that I'm going to be here answering questions for people. So if you leave, you might be missing that. Though this is going to be on YouTube. So if people ask me questions after you leave, I'm going to load it on YouTube. I'm going to try to do it today, as long as there's no problem with YouTube. So you'll be able to see it on YouTube later today. Okay, if you leave now. Okay, so if you need to go, you can go. Thank you for being here. Again, the test is tomorrow morning at 10 a.m. There's one student taking the exam at Special Services. You should have received an email, and then you're taking it with them, separate from me. Okay, you have a 1.5 times because you got to confirm that you need that time. But you won't be meeting, that one student will not be meeting with me. I'll be meeting with Office of Student Services, the link they send you. Okay, everyone else other than that one student, you're attending class as normal, the normal Zoom link, and we're taking the exam there. Okay, so if you need to go, you can go. If you want to stay, I'm going to wait a minute, okay, from now, and then we'll start. So think of your questions, and then we're going to start in 1 minute, okay, with the further review, and it'll be on YouTube if you need to see it later. Okay, so I'm going to just mark this off. I'm going to stop the screen share now. Okay, so we're going to wait 1 minute. I'm going to go get a drink of water. I'll be back in 1 minute, and then we'll do a review if you want further review. Okay, I'll be right back. 1 minute. Okay, just drink some water. Okay, there's 2 people here. Okay, so what questions do you have? Okay, you can talk out loud. You can type in the chat if you want. So this is for you, right? So I'm not, it's not a lesson, so I'm addressing questions you have. So either of you have questions? Okay, sure. Okay, question 3 from homework 1. Okay, so I got all the homeworks here. Question 3. So you mean this is your question, right? Where's the chat? I'm going to put that back up. Can we do, yes, okay, good, okay. Zoom acts weird sometimes. Okay, so there's this question. Let A, B, and C be events of a sample space. Which of the following are true statements? A and A prime are mutually exclusive events. Okay, so you answer for me. The mutually exclusive events mean that they cannot happen at the same time, right? Can A and A prime happen at the same time? Marusha, can A and A prime happen at the same time?
I think no.
No, right? So are A and A prime mutually exclusive events?
Yes.
They are, right? Mutually exclusive events are events that cannot happen at the same time. A and not A cannot happen at the same time. You can't have a sample point in the sample space both be in an event and not be in an event. And so these two things are mutually exclusive events. Okay, so we're good there. So the answer is that they are mutually exclusive. The check is that we did the problem. Okay. If A and B are mutually exclusive, then A prime and B prime are mutually exclusive. Okay, that's a little bit harder. So the assumption is that A and B are mutually exclusive. And the statement is saying that A prime and B prime are mutually exclusive. So let's look at a Venn diagram. Venn diagrams are really good at visualizing the relationships between different things. And so here, this Venn diagram, this circle A and this circle B is illustrating the relationship between A and B. So we have we have the sample space S, then we have events A and B, right? But okay, so A and B are mutually exclusive. So actually, I'm gonna separate the two circles to I wouldn't have to. I could put nothing in the intersection, but I want to exaggerate the fact that they're disjoint. Okay, so here's A and here's B, and they're mutually exclusive events, right? Event is a subset of the sample space. So they're disjoint subsets of the sample space. Then now it's asking, what about A prime and B prime? Are they mutually exclusive? So what I want to do is I'm gonna highlight A prime. I'm gonna highlight A prime as red. Okay, so this is A prime. Okay, so Marusha, do you agree with me that that's A prime? The red part?
Yes.
Okay, good. Now B prime, I'm going to highlight as blue. So everything not in B, I'm going to make blue. This is also not in B, so this is blue. So A prime and B prime blue. So the question is A prime and are A prime and B prime mutually exclusive? And so the question of whether A prime and B prime are mutually exclusive is asking the question, is the intersection of the two the empty set? That's the question, right? If the intersection of A prime and B prime is the empty set, then they are mutually exclusive. If it's not equal to the empty set, if it's not empty, then they're not mutually exclusive. So Marusha, is the intersection of the red region and the blue region, is the intersection of A prime and B prime, is it empty or does it have non-empty intersection?
No, it's not empty.
It's not empty, right? And so the fact that A prime intersection B prime does not equal the empty set, that implies what? That A prime and B prime are or are not mutually exclusive?
They are not mutually exclusive.
Correct, are not mutually exclusive. There we go. A prime and B prime are not mutually exclusive. So, okay, let's go back to here. Okay, so now we answered B. A prime and B prime are not mutually exclusive. So by the check, I mean that we did the problem. But let me, instead of putting checks, I'm going to put true or false. Okay, this is true. And the next statement is false, right? So we showed on the whiteboard that this is false. Okay. Okay, for C, if the occurrence of A implies the occurrence of B, then the occurrence of A prime implies the occurrence of B prime. Okay, so let's look at that. So I'm going to do here is I'm going to copy this. Again, this is a relationship between sets, and so we're going to use a Venn diagram again. If for these kind of questions that you're having trouble with, these questions are good for a Venn diagram. So I'm going to put in the here. This is the statement, right? This is either true or false, right? Not both, right? So I'm not saying this is true. The question is whether or not this is true. Okay. Okay, so the question is I'm not saying this is true. The question is, is the following statement true or false? Right, that's the question. Is the following statement true or false? If the occurrence of A implies the occurrence of B, then the occurrence of A prime implies the occurrence of B prime. So we're going to use Venn diagrams. So I'm going to use red for A. Okay, so the relationship between A and B here is that if A occurs, then B occurs. So as a set, the set A would be entirely contained in the set B. Okay, the occurrence of A implies the occurrence of B. A and B are events. They're subsets of the sample space. And so if you're looking at the entire sample space S, A and B are subsets, but every time A occurs, B does. So that means the set A is a subset of set B. That makes sense? Now, A prime, I'm going to denote by brown. So A prime is this. A prime is everything outside of the circle, the red circle. Right? That includes both inside and outside the purple, right? That's A prime. Okay, and now let's go with light blue for the occurrence of B prime. So for B prime, it's everything not in B. So that's this region, right? This is what's not in B. It's not going over the black line. It's just, okay? So, so it's asking, does the occurrence of A prime imply the occurrence of B? So the question of whether or not the occurrence of A prime implies the occurrence of B prime. What that means is it's asking the question, is A prime a subset of B prime? Right? Does the occurrence of A prime imply the occurrence of B prime? That's asking, is A prime a subset of B prime? Because A prime a subset of B prime means that the event A, any sample point in the event A prime is also in the event B prime, meaning the occurrence of A prime implies the occurrence of B prime. So here, A prime, again, is the brown region, and teal is the event B prime. So is the brown region a subset of the teal region? Marusha?
I'm not sure about this because because some part is intersecting together, like of A prime and B prime. So I guess let's say yes. I think it's yes.
You see that A is a subset of B, right? You get that?
Yeah, I get that.
Okay, so now let's look at, I'm going to draw this picture. I'm going to try to draw it better. Okay, so here's A, right? And so A prime, I denoted with brown. So I'm going to do it in my hand. This is A prime, right? Right, that's A prime?
Yes.
Okay, we want to know whether A prime is entirely contained in B prime. Okay, so as I'm drawing, I want you to figure out while I'm drawing it. Okay, A prime, I want to know whether this brown region is contained in the teal region I'm about to draw. Okay, so first I'm going to draw the set B, right? A implies the occurrence of B, and that means that circle B entirely contains circle A. That makes sense?
Yes.
Okay, now B prime is the complement of that purple circle pink circle I just drew. Okay, so now I'm going to shade in B prime. Okay, now what I want you to do is I want you to tell me whether or not the brown region, not contained, so I want you to tell me whether or not the brown region is entirely inside of the next region I'm going to draw. Okay, I'm going to draw a teal region, the complement to B, and I want you to tell me, is the brown region entirely inside of it, inside of this, okay? Inside of it. This is B complement, B prime, the teal region. Oh, my hand. This is B prime, this is the teal region. Is the brown region entirely inside? Is the brown region entirely inside of the teal region?
No, it's not entirely inside because some of
Exactly,
the
so A prime is not a subset of B prime. Does that make sense?
yeah, I get it.
Okay, so the answer is no. No, A prime, the brown region, is not entirely contained in B prime, the teal region. And so since A prime is not a subset of B prime, that means that A prime, the occurrence of A prime does not imply the occurrence of B prime. And so with that assumption, the conclusion does not happen. And so this statement is false. That makes sense?
Yes.
Okay. So what happened is in this problem, okay, so now we're going to put an F for false. What happened in this problem is we have an if-then statement. We have if the occurrence of A implies the occurrence of B, if the occurrence of A implies the occurrence of B, then the occurrence of A prime implies the occurrence of B prime, right? The first thing I underline is the assumption. The other thing I underline is the conclusion, right? To show an if-then statement is false, you have to say that given the assumption is true, show that the conclusion is false. So if you have an if-then statement, if the assumption, then the conclusion, if the assumption, then the conclusion, to show that the assumption can be true and the conclusion can be false, would then mean that the if-then statement itself is false. Does that make sense? So that's what we did. Okay. To show it's false, you show the assumption is true and the conclusion is false. Okay. If the occurrence of A implies the occurrence of B, then A and B prime are mutually exclusive events. Okay, so I'm going to copy this. If the occurrence of A implies the occurrence of B, then A and B prime are mutually exclusive events. Okay, and so now we're going to go to the whiteboard again. I'm going to put in the text here and make this black. Okay, and then so remember the question is asking, is the following statement true or false? I'm going to make this red. Is the following statement true or false? Oh, it was blue before. Okay, I want to stay consistent. Let me make this blue. Is the following statement true or false? Okay, if the occurrence of A implies the occurrence of B, then A and B prime are mutually exclusive. Okay, so A is red and pink. Okay, so red. So A implies the occurrence of B. So A is a subset of B. Still the same there. And you have the universal set. You have the sample space, S. A and B are subsets. Sample space is events. A implies occurrence of B. That's the assumption. Then A and B prime are mutually exclusive. So B prime, I'm going to denote by this purple. Okay? So B prime is everything not in that circle B, right? And A, I denoted by red. And so now I'm going to shade in the circle inside the circle because I want to consider the set A. So is it true that A and B prime are mutually exclusive events?
Yes, it's true.
It is, right? Because A intersection B prime is equal to the empty set, the disjoint. So that implies that A and B prime are mutually exclusive. Okay, so A, B prime are mutually exclusive. And so saying A and B prime are mutually exclusive. And so this is true. Okay, so D is true. E, if A and B are mutually exclusive and B and C are mutually exclusive, then A and C are mutually exclusive. Okay, is the following statement true or false, right? I'm not saying this is true. I'm not saying it's false. It's one or the other, right? Okay. If A and B are mutually exclusive and B and C are mutually exclusive, then A and C are mutually exclusive. Okay, so if we want to prove this true, we would need like a full justification for it. No, it's still a full justification what I'm about to say, but it's different. If you can show a counterexample, then that's called proof by counterexample, and you can show it's false. So if A and B are mutually exclusive as events, that means the circle A and the circle B are disjoint, right? The events and they're disjoint sets as subsets of the sample space. So A and B are mutually exclusive. Check, right? Because I have them disjoint here. And B and C are mutually exclusive. Right? And now I need a circle C that's disjoint from B. How about I do this? B and C are also mutually exclusive, right? Because B and C do not intersect. So A and B are mutually exclusive because they do not intersect. B and C are mutually exclusive because they do not intersect. But the way I drew it, I made it so that A and C do intersect. And so now A and C are mutually exclusive. Is that true or false? Marusha?
I think it's false even though like the intersection, I don't, I think
Look
that
at the
set
picture.
is
Look,
empty set, so it is mutually exclusive.
no, see the picture here?
Yes,
Is A intersection C in the ones I chose, is that empty? Is that equal to empty set or does not equal?
I think it's an empty set like this.
No, sorry?
It is an empty set. It is empty.
It's not, right? You said not?
Um,
Do circles A and C overlap here?
yes, they do overlap, but I thought that's still because there isn't anything in it, so it's empty.
Well, no, so just look at the picture, right? Forget about everything else you're thinking. Do these two circles overlap?
Yes,
When two circles overlap, are they empty or not empty?
they're not empty.
Right. I mean, you could put nothing in it, but I'm saying that there's something in the intersection. So
Yeah.
they're not equal to empty set. So what does that imply? Does that imply that A and B are mutually exclusive or not?
They're not mutually exclusive.
Right. A, B, not mutually exclusive, right? Okay. So sometimes when you think something we're right, sometimes we're wrong, right? But if you're following the trail of mathematics and the math is showing you something, even if you think something's true, what you have right in front of you might be showing you, all right, it's false. What I was thinking was wrong. I have to change it, right? So here, the picture I drew, it's a proof, right? I'm proving to you that this statement's false, right? If a proof is correct, then if you're reading a proof and you think something and you're reading a proof and there's nothing wrong with the proof and the proof's right, then that means you're wrong. Does that make sense?
Yes.
Okay, so here, do you agree with me that circles A and B are disjoint?
With circles?
Do you agree with me that circles A and B in the picture are disjoint?
Yes.
They're separate, right? So you see how A and B are mutually exclusive here?
Yes. Yes.
Right? B and C are mutually exclusive. Do you agree with me that B and C as circles are disjoint?
Yes.
They don't overlap, right? So do you agree with me that I've met the conditions of the problem that A and B are mutually exclusive and B and C are?
Yes.
Right? Then the statement says A and C are mutually exclusive. But in my example, A and C are not mutually exclusive, right? They overlap. See that?
Yeah. Yeah.
So this is a counter example. So this is a counter example. A counter example is finding something that could happen that contradicts a statement someone makes. Right? It's like if somebody were to tell you it's raining right now. And then I walked over to the window and I opened it and I said, look, there's no rain outside. I proved you wrong. I've shown you something that shows that you're wrong. Does that make sense?
Yes, it makes sense.
So this is a counterexample saying that if someone walked up to me and said, if A and B are mutually exclusive events and B and C are mutually exclusive events, then A and C are mutually exclusive events. I would say, look at this Venn diagram. See that? And then the person say, oh, wait, that's wrong. Does that make sense?
Yes, it makes sense.
Okay, so proving something wrong is sometimes much easier than proving something's true or right? Saying sometimes saying somebody's wrong is just saying, well, here's an example where that doesn't work, right? And then it's false, right? So this statement is false because I found one situation where it doesn't work. Okay, it's really because of the type of statement. This is a very big statement to make because it's talking about relationships, but it's saying that always. It's like whenever A and B are mutually exclusive and whenever B and C are mutually exclusive, A and C are also mutually exclusive. It's a very broad general statement. And so to show it's false, I only need one situation where it doesn't work. And so one counterexample is enough to say that this very broad statement is false. Make sense?
Yes.
Okay, good. Okay, so this statement is false. It's false. And it's false by counterexample. The proof method is called proof by counterexample. So this is false because we showed a counterexample. Okay, so let's go back here. So E is false. Okay, so there's a good alternation of true and false. It goes true, false, false, true, false. Okay, so now F, if A and B are mutually exclusive, then the occurrence of A implies the occurrence of B prime. This is the last one. This is F. So if A and B are mutually exclusive, then the occurrence of A implies the occurrence of B prime. Okay, if A and B are mutually exclusive, then the occurrence of A implies the occurrence of B. Okay, so here's A, and here's B. They're mutually exclusive, right? And so that means that they don't overlap. So that means that they're separate, that they're disjoint as subsets of the sample space, right? That makes sense?
Yes.
Okay, good. So if A and B are mutually exclusive, check. We covered that in this picture, Venn diagram. Then the occurrence of A implies the occurrence of B. The occurrence of A implies the occurrence of B. What that means, the occurrence of A implies the occurrence of B. Oh, it implies the occurrence of B prime. That statement is saying that A is a subset of B prime. Does that make sense?
Yes.
Because A implies the occurrence of B prime means that every sample point in the event A, every simple outcome of the event A is also in the event B prime. Anytime something happens that's in the event A, it has to also be in the event B prime. So A has to be a subset B prime. Okay, so A is this set. And now B prime is the complement of B. And so I'm going to denote the complement of B by this, okay? This is B prime. Right? So is A a subset of B prime? Is the red region a subset of the pink region?
Yes.
It is, right? It is. A is a subset of B prime. So if A and B are mutually exclusive, if they're disjoint subsets of the sample space, if A and B are disjoint subsets of the sample space, then the set A is a subset of the set B prime. That's true. And so this is true. That makes sense?
Yes.
There we go. And so that's true. So now let's go back here. And this is true. Okay? And so we have true, false, false, true, false, true. And so those are the answers to A through F in number 3. Okay, so does that answer your question completely? Is there anything else in number 3 that you don't get? Or
No, I understand everything. Thank you.
oh, good. Okay, good. Are there other questions, or can we stop there? I'm kind of tired. We good? Okay, so I answered all the questions I saw. So we'll stop here. Good luck on the test tomorrow. I'm just going to save the whiteboard. Oh, wait. PDF. Okay, good. Okay, so if you guys want to see this stuff again, it's going to be on YouTube. It just needs to download first. Okay, I got it. Okay, so okay, I'm gonna end this now, and then if you want to look at this stuff again, in a few hours, it'll be on YouTube. And then the lesson notes and the whiteboard notes will be on Blackboard. Okay? Okay, bye. See you tomorrow morning. Thank you for attending. Bye.